Here is an example of solving a Yucky inequality and how we can organize our data in an efficient fashion. This is the problem we're going to tackle. X squared minus 5x minus 14 over x plus 6 is the function, and we are going to discover where that function is less than or equal to 0, and we're going to represent that solution set properly. Now, the difference between inequalities and equations is that equations where it's equals 0, you come back with like a couple of numbers that are the solutions, or maybe none. But with inequalities, we are looking for entire stretches of the number line where you find x values which will make the equation true. And so that's a little bit more of a nuisance. And the notation that we're going to use to present the answer is pretty important. So just real quickly here, like if we did solve a problem and we decided that one stretch of the number line between 0 and 4, with 4 actually included in the set but -2 not included, but also every number larger than 5. I'm just now noticing that I wrote 10 in the paragraph and put 5 in the interval notation. So we want all the numbers larger than 5 to be included in the solution set. Then what's displayed on the screen, the interval -2 to 4 with a square bracket on the 4 to denote that endpoint is included. We have the interval from 5 to infinity, which means everything bigger than 5 that there is, and the big giant union sign joining those two together to make them one set. That's the collection of all numbers that would make that hypothetical problem true. Okay, so you kind of need to be good with that sort of notation, and we're not going to stop and break it down here. I'm assuming if you're trying to solve inequalities that you've seen this kind of notation before. All right, so the nasty problem that we're going to solve, which remember was this one, is a function or an inequality of the form, here's a function, we're discovering where it's less than or equal to 0. So think about what graphs like that might look like, and what we're going to look for just in a visual sense. Right? So here is a sample. This is just some function. It's not the one that we're talking about. But suppose there's a graph of our function up here at the top, and the red arc is where we see that the function lives below the x-axis. There's two pieces in red, so there are two places where this function is below the x-axis, and so those two intervals from minus infinity up to whatever this value is, and then between these other two values, that joined unioned set is going to be the full solution to this function less than or equal to 0 as an inequality. Okay. So stretches of the axis where the graph of the function is above the axis help solve f of x is greater than 0. Where the graph is below the axis, that's where we see f of x is less than 0. And the thing to keep in mind, and this is going to be a big help in always solving these things, is that the points where we transition from f of x less than 0, the red, to f of x greater than 0, the blue, the points where we make that transition are the points where the function is equal to 0. And that is crucial. Okay. Now, I haven't talked about that lower graph, and that's because there's an open question here. Is that, are there other locations where a function might suddenly switch from being less than 0 to being greater than 0, or vice versa? Not just places where the function is equal to 0. The answer is yes. And so this second picture is an example of that. I'm sure you've seen graphs like this before. This is a graph with an asymptote. The blue section is f of x greater than 0. The red arc is f of x less than 0. So it does switch from one to the other, but there is nowhere on this graph where f of x is equal to 0. However, the break happens at the discontinuity. Okay, so transitions between a function being greater than or less than 0 can happen when the function is equal to 0, or it can happen when there's a discontinuity. And if we do have a point like one of these in the top graph where the function is equal to 0, that doesn't necessarily mean that it has to transition from greater than 0 to less than 0. It means it's possible that it could change from greater than 0 to less than 0. It could be that the graph just comes down, hits that point, rebounds, and goes right back up again so that it's greater than 0 everywhere except for that one point where it was equal to 0. But at least we have the points where that transition might happen. And that's going to be the key to solving these problems. Okay, so what we're going to do is we're going to get our inequality, f of x is less than or equal to 0, and we're going to look for values of x where the function is equal to 0. Okay, we're going to find values of x, if any of them, where there's a discontinuity. And those are going to be our suspects, our locations where the function might move from greater than 0 to less than 0. And those are going to delineate the intervals that we want or don't want. Okay? And so we're going to place all these points where the function is equal to 0 or where it has a discontinuity as markers on the x-axis. And we're going to look at the intervals in between those markers and figure out which intervals are the winners according to whatever discontinuity or whatever inequality that we have. So we're going to start with a really simple one, actually, not the fancy one that we aimed at the beginning. We'll get to that in a minute. But this is about organizing data. So I want to make sure to show how we're going to do that. Oh, good, the dog is barking. They always know when I'm recording a video. But we're going to take the easy function 1 minus x squared. And we're going to ask, where is that less than 0? Okay, well, here's a picture, right? You know that f of x is 1 minus x squared is an upside down parabola. It's badly drawn by me on this picture, but we're not going to look at it for very long. The stretches in red are the stretches where the function is less than 0. And we certainly know that 1 minus x squared hits 0 at -1 and 1. And so from negative infinity up to -1, the function is less than 0. From 1 on out to positive infinity, the function is also less than 0. And it's greater than 0 in between -1 and 1. Okay, so just from the picture, we already know what we're looking at when we're asking where is 1 minus x squared less than 0. But we're going to go through the process just to get used to the bookkeeping. Okay, so the values where 1 minus x squared is 0 are -1 and 1. Which means we're going to place those points as markers on the number line, the x-axis from minus infinity to infinity. From your perspective, probably minus infinity to infinity. And that's going to leave us with 3 subintervals to look at. Okay? And on each of those intervals, subintervals, we're going to test whether the function would be positive or negative in those intervals, subintervals. Okay, and that's going to that can be organized this way. So I've written the function as 1 minus x squared is less than 0, and I've even factored 1 minus x squared into 1 minus x times 1 plus x. And I'm doing this to get you used to the bookkeeping method here. I've drawn a number line, and I've put markers there at -1 and 1. Okay, and here's what we're going to do. There's 3 intervals on the number line now that are delineated here, and for each interval, we're just going to jot down what's the sign of 1 minus x? Is it positive or negative there? What's the sign of 1 plus x? Is it positive or negative there? And then given those 2 pieces of information, what would be the sign of 1 minus x squared? Because that's what we're looking for, right? That's what we're after, to find out where 1 minus x squared is less than 0. Okay, so from negative infinity up to -1, so like -1.1, -5, -872, negative the national debt. Okay, whatever those numbers are, that's the interval we're after. For any number from that interval, if we do 1 minus that number, we are going to have a positive result, right? 1 minus -2 is 3. 1 minus -2 is 3, right? So when we do 1 minus negative numbers in magnitude on the number line less than -1, we're going to end up with a positive result. Even if the number is -1.00001, 1 minus that is going to be positive. Okay? 1 plus that number, well, that's going to be negative, because it's 1 plus a negative number that has size bigger than 1, although it's negative. So like 1 plus negative 2, negative. 1 plus negative 80, negative. 1 plus negative 1.00001, negative. Not by much, but it's negative. Now, 1 minus x squared is just the product of 1 minus x and 1 plus x. So if 1 minus x is positive, 1 plus x is negative, 1 minus x squared, the product of those two numbers, is going to be negative. Okay? For numbers between negative 1 and 1, like 0, 1 minus x will be positive. 1 plus x will be positive. Now, we could be like right about here, like negative 0.999, but 1 plus negative 0.999 is still positive, only by a little bit, but it's still positive, right? And so since 1 minus x squared is the product of those two numbers, it's always going to be positive in that interval. And now for numbers bigger than 1, 1 minus x is certainly going to be negative now. 1 plus x is certainly going to be positive, and the product of those two would be negative. Okay, and there we go. There are the two intervals that cause 1 minus x squared to be less than 0, and so we would present the solution set as an interval from negative infinity up to negative 1. We would also have the interval from 1 to infinity, and when you have two disjoint intervals like that, you clip them together in a solution set with the union symbol. Okay, so that would be our answer. So that's an easy problem just to look at the bookkeeping. So the main event, here we go. X squared minus 5x minus 14 over x plus 6 less than 0. I am factoring the numerator here. I think you can trust me that this factoring is correct. And so that's a factored version of our inequality. And so let's start looking for our number line markers. Now, points where the function on the left-hand side there is going to be 0. Those are easy to diagnose from the factored version, right? When x is 7, the numerator is going to be 0, so the function is 0. When x is negative 2, numerator is 0, the function is 0. Okay, so those are important points. However, remember the discussion that we have to also look for discontinuities. In 1 minus x squared, there aren't any. But in this function, there is a discontinuity because of that denominator x plus 6. When x is negative 6, you have bad news for that function. You have an asymptote. So there are 3 important markers on the number line. And I've put them in order. Okay, so we're going to split the x-axis into 4 pieces. Negative infinity up to negative 6, then negative 6 to negative 2, then negative 2 to 7, and then 7 to infinity. And in each of those intervals, we're going to take a look at the sign, S-I-G-N, not the trigonometric sign, of the term x minus 7, the term x plus 2, and the term x plus 6. And with the signs of each of those individually, we then know the sign of this whole function. And so we'll know the net sign, and we can decide where did we discover that it would be less than 0. Okay, so here comes another diagram. I've got it prepped here. Let me make sure I have a good color that's going to stand out from the rest a little bit. Okay, this is gonna, it's gonna take a minute or two here. We're gonna think about to the left of negative 6. So like all you have to do is pick one representative number and then think about it. So like negative 10. Okay, when we're at negative 10, x minus 7 is going to be negative. If you're already less than negative 6 and you're going to subtract 7, you're definitely going to be negative. X plus 2, if we're over here, well, we're already below negative 6. Adding 2 isn't going to do much. That's still going to be negative. X plus 6, well, we're over here far enough that adding 6 is still going to keep us in negative territory. And so if the function is made of these three hypothetical numbers, 2 multiplied and then divided, it's going to be negative times negative divided by negative. That's three negative signs. The function itself is going to be negative. Okay, let's look in between -6 and -2. Again, we're already negative, so subtracting 7 is certainly going to keep us negative. When we're adding 2, well, we're already to the left of -2, so adding 2 might get us close to 0, but not going to get past it, so that's still going to be negative. And now x plus 6. These are negative numbers like -3, -4, -5.9999. When we add 6, that is enough to get us into positive territory. All right, between -2 and 7, such as 0, x minus 7 will still be negative. X plus 2, well, now it's going to be positive. X plus 6, positive. So the net, whoops, I forgot to do my net in the second column, so let's think of them both. Let's move back to the second column here between -6 and -2. And if we build this function, we're going to have a negative times a negative, which is positive, divided by a positive. The net result is positive. And now, -2 to 7. We'll have a negative times a positive, which is negative, divided by a positive, the whole thing, negative. And now for numbers bigger than 7, everything's going to be positive, right? So positive, 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 and the whole function positive. Okay, so the original inequality was we were looking for where that function is less than or equal to 0, and our winners are this interval and this interval. So -infinity up to -6, -2 to 7, and we're going to clip those two together. And so that's the result. Or is it? There is a subtle detail here. We just discovered the intervals where this particular function is less than 0. The actual problem would like us to know where that function is less than 0 or equal to 0. Now that second part is kind of a footnote because it's pretty simple, right? Remember that the function is x minus 7 times x plus 2 over x plus 6. Okay, so where will this end up being 0? Well, when we plug in x equals 7, okay, we would get 0, so we need to include 7. And when we plug in -2, this function would be 0. So we need to include -2 and 7, which means in our interval presentation of the answer, we change the rounded brackets to square brackets to indicate that those endpoints are actually included in the final result. Okay, and now we're done. However, I'm going to pause real quick, not for you, just for me, and I'm going to actually pull up a plot of this function so we can take a look and make sure it's consistent. And if it's not, then I got to go back and do this whole thing all over again. And here we are. On the scale of the axes that Wolfram Alpha is giving, it's a little hard to see, but certainly here's a wing of the function over here to the left of what would be the asymptote. So the -infinity up to -6, the function is definitely less than 0 there. And then you can kind of see right through here that from -2 up to 7, that graph has dipped below the axis just a little bit, but it is below. And so that -2 to 7 is still valid. And again, we want the endpoints of -2 and 7 included because the original problem specified this function needs to be less than or equal to 0.